enterprise architecture in C# can easily spiral into an unmanageable web of tightly coupled dependencies. Today, we're exploring the 5 principles of Solid. We're going to systematically demystify how these specific design principles transform brittle, failing applications into robust, highly modular ecosystems. By addressing specific code smells with precise refactoring techniques, we can build systems that scale elegantly and completely resist regression. Think of Solid as a kind of clinical blueprint. It's the cure for that monolithic legacy spaghetti code we've all wrestled with. It's really a journey from a chaotic, tangled mess, passing through 5 distinct filters and emerging as a beautifully structured, interconnected ecosystem. Each filter serves a unique purpose. It isolates, extends, substitutes, segregates, and inverts. Okay, let's dive directly into this process and examine the first crucial filter. The S in Solid stands for the Single Responsibility Principle, or SRP. Treating a class like a multi-tool is honestly the core fallacy of poor class design. When a single tool tries to be a hammer, a blowtorch, and a computer mouse all at the same time, it naturally becomes fragile. It just has way too many failure points. True enterprise integrity relies on a discrete tool belt. A class should have exactly one reason to change. If your class processes data and also logs data, well, it's already doing too much. We can clearly diagnose this exact problem by looking at a real C# environment. Take a careful look at the order service class. We have business logic calculating a discount mixed right in with a direct SQL connection inserting data into a database, which is then mixed again with an SMTP client sending out an email. If we methodically trace the dependencies here, the code smells pop up immediately. If our database schema updates, this class breaks. If we switch our email provider, this exact same class has to be modified. It's a completely overworked service with multiple conflicting reasons to change. The refactoring solution here is simply to delegate these distinct responsibilities. We now have an order processor that solely handles our core logic, relying purely on abstractions. The persistence logic is completely moved out into a dedicated SQL order repository, and the communication logic is safely isolated inside an email notifier. The enterprise impact here is huge. Changes to the email system now carry absolutely zero risk of breaking your order processing logic. Your testing can focus strictly on business rules without constantly worrying about firing off phantom emails. Let's move right along to the O in Solid and see how this builds our foundation. This is the open-closed principle. I want you to think of your software architecture kind of like a computer motherboard. We know the danger of modifying existing working systems. It's honestly like trying to solder a brand new chip directly onto a live board. It carries a remarkably high risk of destroying your existing logic. Instead, what we really want are plug-and-play extensions. Software entities should be open for extension, but entirely closed for modification. Let's carefully examine how this exact violation shows up in everyday C# code. Check out this payment processor. We have this really fragile if-else block checking if the payment type is credit card or PayPal. This right here is a massive red flag. Ask yourself, what happens when the business suddenly wants to add crypto payments tomorrow? Well, you'd have to open up this exact class and modify core, tested production code just to add another else-if statement. The bug risk basically increases linearly with every single addition you make to this block. To properly cure this, we close the core. We introduce an iPayment method interface with a simple standardized process contract. Now, credit card payment and crypto payment are just independent classes that implement this interface. By applying the strategy pattern here, we empower the entire system to scale infinitely to new payment types. Months down the line, you can easily add a new payment gateway with zero changes to your core logic, completely bypassing the need to trigger expensive regression testing on those legacy payment methods. Our next step takes us to the L, the Liskov Substitution Principle. What we're looking at here is a classic runtime minefield. We have an abstract product class with a ship item method. Physical product inherits from it perfectly. But then we introduce a digital product. Because it inherits from product, it's strictly forced to implement ship item, but obviously you can't physically ship a digital file, so the developer throws a not implemented exception. This completely destroys the base class contract. A loop calling ship item across a list of all products will eventually hit that digital product and inevitably crash your entire application at runtime. The elegant fix is to prioritize capability over taxonomy. Instead of forcing a rigid, unnatural hierarchy, we simply separate our contracts. We create an iProduct interface for general properties like name and price, and a completely distinct iShippable interface specifically for the act of shipping. Physical product implements both. Digital product implements only I product. The result? True polymorphism is restored. Your batch processing loops can now safely operate on a list of I shippable items without ever needing cumbersome try-catch block safety nets. This crucial point actually seamlessly carries over into our the interface segregation principle. A bloated, fat interface is literally like a massive, confusing remote control. It just burdens clients with a staggering array of buttons and irrelevant dependencies that they are never, ever going to use. We want the sleek, segregated remote, high cohesion, exact fit. Clients should never be forced to implement methods they simply do not use. Methodically diagnosing this in C#, we frequently encounter what's known as the God interface. Take a look at I order operations. It demands process payment, print shipping label, and restock inventory. Now look at our warehouse worker class. To satisfy this contract, the warehouse worker writes perfectly valid logic for shipping, but is then forced to write dummy methods throwing exceptions for processing payments and restocking, purely just to get the code to compile. The worker is unfairly burdened with financial and inventory dependencies, severely violating cohesion and massively increasing tight coupling across the system. We resolve this through role-based contracts. We take that God interface and split it into I financial operations and I fulfillment operations. Now, our warehouse worker elegantly implements only I fulfillment operations, allowing us to write clean, precise code without a single dummy method in sight. The architectural payoff here is immense. This is the very foundation of robust microservice architecture. Your system components only import the exact packages and interfaces they truly require, drastically reducing ripple effects during massive refactoring efforts. Finally, we reach our last letter, D, the Dependency Inversion Principle. Imagine buying a new lamp for your living room and having to literally solder its wires directly into the structural wiring inside your wall. That is hardwiring. The high-level module is inextricably bound to the low-level details. Instead, what do? We use an abstraction, the standard wall socket. Both the lamp and the wall depend on that standardized abstraction. The rule here is simple. High-level modules should never depend on low-level modules. In our C# architecture, the soldering iron is actually the new keyword. Look at the order processing service. It is instantiating SQL database service and Stripe payment gateway directly inside the class itself. These are concrete, hard-coded dependencies. This service is now eternally welded to SQL and Stripe. More importantly, attempting to test this checkout logic in isolation without actually hitting a real live database or accidentally charging a real credit card is completely impossible. You are entirely trapped by your own instantiations. The clear cure for this is to invert control. Notice the green flag in our refactored code. We define abstractions, iDatabase service and iPayment gateway. We then inject these dependencies directly into the order processing service through its constructor. The class no longer creates its own tools. They are simply handed to it. This inversion of control is truly transformative. It completely unlocks dependency injection. Your code becomes instantly unit testable because you can now seamlessly pass in mock objects, like a mock database service, right through the constructor. To synthesize this entire clinical teardown, let's take a look at the solid diagnostic matrix. Think of this as your go-to reference guide. When you see a class handling UI, data, and logging all at once, that's an SRP violation. Your cure is extracting responsibilities, which is beautifully supported by the facade pattern. When you see endless switch or if-type checks, OCP is practically crying out for the strategy pattern. When derived classes throw non-implemented exceptions, LSP requires behavioral capability mapping. Dummy methods, those point straight to ISP failures, curable via role-based microinterfaces. And finally, the new keyword deeply embedded inside business logic demands DIP, perfectly solved by constructor injection. We've mapped out the symptoms to their exact architectural cures, replacing fragile spaghetti code with resilient modular ecosystems. So I'm going to leave you with this final critical thought to ponder. Look closely at your own current C# code base today. Which of these 5 specific code smells is currently hiding in your classes, silently risking the stability